F322 June 2012, question 4. This question is going to take you through a bit of enthalpy and a bit of green chemistry, a bit of a mixture here. We've got catalysts again, and we've got the Haber process. So nitrogen and hydrogen reacting together here, and it's given you the enthalpy change for the forward reaction as minus 92 kilojoules per mole. Now, whilst we're looking at this equation, the first question in this part A is going to ask you, well, here's the enthalpy change to produce 2 moles of ammonia, and it's minus 92 kilojoules per mole. How many, or what would the enthalpy change for the delta H of formation of ammonia? So this first question is essentially asking you, what is the definition, first of all, for the enthalpy change of formation? Try it out now. So we've got P, enthalpy of formation, 1 mole of a substance being formed from its elements. Here we've got 2 moles being formed. So the answer to our first question, we just want 1 mole to be formed, it will produce half of this value. So that's our answer to the first question. We'll come to it in a second. The next question is going to be looking at activation energy. Here it's given us the activation for the forward reaction is plus 250. So let's just put this on the diagram here. Because, first of all, I'm jumping ahead of myself, you've got to complete the enthalpy profile for the reaction between nitrogen and hydrogen. It tells you what it wants, products, enthalpy change, delta H, and the activation energy. So, first of all, our products, and where are the products and where are the reactants? Here we've got a minus sign, so exothermic reaction energy is being released, so the enthalpy change is negative, so it's going down, so you've got reactants higher than products. So we draw our diagram like that. It's given you the axes, you put the products on, so we've got 2NH3, you've got the enthalpy change here, which I'll just add on as being minus 92, where that black lines come from. Then you've got this as plus the activation energy plus 250. So that is minus 92. I don't know why that's go away. Minus 92. Okay. So here for your marks, delta H is labelled with the product below the reactant and product as 2NH3 for your mark there. Then, as I've said earlier, going on down, they're asking you what is the value of the enthalpy change of formation of ammonia. As I've said, since you're given the enthalpy change minus 92 for 2 moles, your enthalpy of formation is only ever for 1 mole, and so you're dividing that by 2 and you get minus 46. Then it asks, quite a cheeky question this one really, for the reaction between nitrogen and hydrogen, you can use a catalyst. Suggest a possible value for the activation energy of the catalyzed forward reaction. Here it's actually just looking for the definition of a catalyst. A catalyst lowers the activation energy. So your answer can be anything from +1 to 249, as long as you've still got an activation energy and it's lower than the activation energy that they gave you in the question of 250. So that one, any value there between +1 and 249. Just for a moment, you should know what the catalyst would be here for the Haber process. Nitrogen and hydrogen is catalyzed by, should know that it's catalyzed by iron. Now, people always find this one tricky. What's the value of the activation energy for the uncatalyzed reverse reaction? So going back from ammonia to produce nitrogen and hydrogen. So here you've got the answer there of plus 342, but let's just have a look on the profile how we would do it. So essentially what it's saying is, what value would you give if you went the opposite way? So you went back up. Sorry, it's supposed to be a straight arrow. It's not a mechanism, is it? Back up there. So going back up, and it's supposed to be green that as well, you know. Back up there, you've got plus 92 going back that way. Still going curly, look at that. And then you've got your activation energy, which is still the same at plus 250. So 250 plus 92 is what gives you your value of 342. So going back down there, you've got here changing the sign because you're going backwards, plus your 250, which is the activation energy anyway. Over the page then, you've then got 3 sections of green chemistry, and I'm just going to whiz through these really. The first one, we're talking about catalytic converters. We've got nitrogen monoxide reacting with carbon dioxide, and you've got to write that equation. So you've got to know that when you add nitrogen monoxide and carbon dioxide together, you're going to make carbon dioxide and nitrogen. So toxic products, or 2 toxic products, things that we don't want. These producing radicals, this being toxic, bad for respiration. We've got these 2 toxic products producing nitrogen, harmless, and carbon dioxide. Harmless in the sense it's not toxic to us, even if it is a contributor to the greenhouse effect. Just a reminder, carbon monoxide, you need to know how that causes us to, can't think what I want to say, that is going to cause respiratory problems because it binds to our hemoglobin. It's an irreversible binding, and so it stops the oxygen from binding to our hemoglobin in our red blood cells, and so reduces our blood's oxygen carrying capacity, which obviously causes asphyxiation in severe cases. Outline the stages that allow nitrogen monoxide and carbon dioxide to react. Here we've got then, this is a classic 3-mark answer. Molecules are adsorbed with that D for adsorbed onto the catalyst. This weakens the bonds, so that's the key thing there. And then the products, and it's often good to use the actual products that there are, so the CO2 and the N2 desorb, and that is a standard model answer for answering the question about a catalytic converter. It might be that they give you different products, different reactants, different problem materials to react, but the 3 marks will be the same. Adsorbed, weakens bonds, desorbed. It's just your job to put in the reactants and the products as required. Then scientists monitor pollutant gases in the atmosphere, state 2 modern analytical techniques that would you use to monitor pollution. The 2 that we use most often are infrared and mass spec. That's what we've learnt about at AS. You've got also UV spectroscopy, or NMR, or gas chromatography, that is there. But stick to the ones at AS. We've got infrared and mass spectrometry. Then finally we've got international cooperation is important. Why is that? To reduce pollution levels, and again it's a fairly standard answer. Any one of these. Pollution travels across borders, all countries contribute, and that sort of thing. So as long as you've got a few of those up your sleeve for the exam, you shouldn't go wrong. Part D, then, the part before we get on to enthalpy and away from green chemistry. Here we've got our classic ozone question. How does NO contribute to ozone depletion? We've got our starting step where we've got to have O3. So we've always got to have O3 when we start. If we're going to be breaking the ozone down, we always start with O3. And we've got our radical, which in this case is NO. Now, it's got to be broken down. So O3, this radical's got to rip an oxygen atom from it. So that becomes NO2 and oxygen there. Then you've got to remember this, different from radical substitution, the mechanism, we always get this O that comes in. Remember that O comes from just the natural breakdown of oxygen with UV light. So that's where that single O comes from, that normal breakdown. That's added to our radical with its extra oxygen on, because we don't want that in our overall equation. We want to get rid of that, so we put that being a product of our first reaction in as a reactant in our second. We react it with this O. Now we want to get our NO back. That's what we want to do. So to get our NO back, we've got to lose an atom from NO2. So we get NO back again and oxygen again. Cancelling down then, we've got that one and it's back there, and that one is back there. Notice how that's on the right hand side, this one's on the left hand side, so I can cancel it. Same here. And so we then have O3 plus O gives 2 oxygen molecules for our final answer there. That again is another standard green chemistry question. Then looking at part E, Hess's law. This was a nasty question. This first bit, part I, often comes up. So it's given you the equation for the formation of N2O, and it says it's not possible to measure this enthalpy change directly. So this delta H for this transformation here, difficult to measure directly, and it suggests why it's not possible. There's a number of standard things you can say here. One is that the activation is too high, or the rate of reaction is too slow. But in this case, if you just add nitrogen and oxygen together, why can't you make something else? We've already been looking at making NO in the previous question. NO, we could have had NO2, or which we've got here as well. So there's all sorts of different things that could be produced with nitrogen and oxygen, not just N2O. So the way that the mark scheme has looked at this, the reaction forms a mixture of oxides, was the key marking point, or it could form NO, which is what it's done previously. Activation energy too high or rate too slow. This kind of question is a fairly standard one. It's done it for glucose, for example, before, and it's added carbon and hydrogen and oxygen together, and it's asked the same question. Why can you not do this? Why can you not measure it directly? And each time you have activation energy too high in the mark scheme, rate too slow in the mark scheme. And for the glucose case, for example, it's that you would have more likely made from carbon and oxygen, carbon dioxide and water. So it's generally that you won't get the products, or just those products, for that kind of reaction. Activation energy too high, rate too slow has been the standard mark scheme for most years for that question. The data below for part 2 can be used to calculate the enthalpy change of formation of N2O, and this was really quite a nasty question, because if you're a user of your CRAP or FPFR, then it's really difficult to know how to tackle this question. In this case, it's given us the formation of N2O. So we've got nitrogen plus a half oxygen gives N2O. So we're trying to work out what that value is. We've got the formation or the combustion, because it could be either, of carbon to form carbon monoxide, and we've got an equation with both carbon monoxide and N2O in it. And this is the key for drawing your cycle, is that you've got what's been formed. N2O has been formed, and you've got that in that equation. Carbon monoxide has been formed, and you've got that in the equation. So you can put this as your top equation of the cycle, and then you have formation from the elements to N2O and to carbon monoxide. This then allows you to think, right, I'm going to be moving around this cycle, I'm going from here to there, I want to do it by going that way and then along this way. About my arrows. So I'm going to keep this value the same. I'm going to add it to this value with a changed sign because I'm working backwards along the arrow. And so we get a value of plus 82. Doing your shortcut method there, it's very difficult to work out whether you should use one method or the other. Obviously there's only two values here and you're going to take one away from the other, and so it's worth 2 marks. I'd just have a go. If you can't see straight away how to draw your cycle, you do know that one's got to be taken from the other. The question is which one from which. Doing the cycle makes it much clearer how to get there, and it also allows you to pick up possibly 1 mark even if you get it slightly wrong.